Hello and welcome to All Things Quantum. This is a standalone presentation to support the quantum computation presentations that are coming in a series on my channel. You could consider this to be maybe even an introduction to quantum computation, but it just does not confine itself to quantum computation because it is considering all things quantum under the sky. Time and Shiva. Time. Familiar and intimate. We are taken by it. The hours, minutes, seconds, merging to one another. We live in time. Or do we? Shiva dances and time flows. Or does it? In the early universe, at the Big Bang, large and small are one. The largest system is compressed into the smallest size, reaching the highest energies. हिरण्यगर्भः संवर्तताग्रे भूतस्य जातः पतिरेकासीत् स दाधार पृथ्वीं ध्यामुत्तेमां कस्मै देवाय हविषा विधेम. In the beginning was the divinity in his splendor, manifested as the sole lord of land, skies, water, space, and that beneath, and he upheld the earth and the heavens. Time has been the most taken for granted commodity. Waste it, spend it. Think of it as being endless, smooth, never-ending, unidimensionally flowing. Einstein's general theory of relativity changed the notion of flow of time forever. Time can twist, turn, curve, slow down, speed up, just as space can. You have mountains and valleys, planets and stars. They are all variations of matter occupying space. Where does time fit into it all? Einstein's concepts were revolutionary, and that's an understatement. His theories have been experimentally verified. Yes, they have. We use Einstein's GTR all the time, actually an application of it, namely GPS. Gravity is one of the four fundamental interactions. Einstein's general theory of relativity is central to understanding frontier astrophysical phenomena such as black holes, pulsars, quasars, final destiny of stars, the Big Bang, and the universe itself. Gravitational physics is a true frontier science. Its important applications lie at both the largest and smallest distances considered in contemporary physics. On the largest scales, gravitational physics is linked to astrophysics and cosmology. On the smallest scales, it is tied to quantum and elementary particle physics. These two frontiers become one at the Big Bang, where the whole of the observable universe today is compressed into the smallest possible volume. The classical theory of gravity has its direct applications for large-scale distances. Newtonian gravity can therefore be only an approximation to yet more fundamental theory. In 1915, Einstein's quest for a relativistic theory of gravity resulted not in a new force law or a new theory of relativistic gravitational field, but in a profound conceptual revolution in our views of space and time. Einstein saw that all bodies fall with the same acceleration in a gravitational field. This led to an understanding of gravity as the curvature of space-time. Yes, space-time. Gravity is geometry. Space-time. This one word encompasses the four-dimensional union of space and time. Masses curve the fabric of the cosmos. That is, the trajectories along which all masses fall are the straight paths in this curved space-time. In Newtonian theory, the sun exerts a gravitational force on the earth and the earth moves around the sun in response to that force. In GTR, the earth moves on a straight path in that curved spacetime. Black holes. General relativity predicts that a Black hole is created whenever mass is compressed into a volume small enough that the gravitational pull at the surface is too large for anything to escape, including light. The surface that defines a black hole is called event horizon. Mass, information, and even observers can fall through it, but in classical physics, nothing can emerge from it. General relativity predicts that ripples in space-time curvature can propagate with the speed of light through otherwise empty space. These ripples are gravitational waves. Any mass in non-spherical, non-rectilinear motion produces gravitational waves. But gravitational waves are produced most copiously in events such as coalescence of two compact stars, merger of black holes, or the Big Bang. This slide shows the Laser Interferometer Gravitational Wave Observatory LIGO. It is a large-scale physics experiment and the observatory to detect cosmic gravitational waves. Planck's constant h cross characterizes all quantum phenomena. Quantum gravitational phenomena are characterized by the unique combination of Planck's constant, gravitational constant, and the speed of light. Unique combinations of these constants further define the Planck length, the Planck time, the Planck energy, and the Planck density. Einstein's classical theory of gravity is no longer applicable to phenomena characterized by these scales because significant quantum fluctuations in the classical geometry of spacetime can be expected. In these regimes, Einstein's theory needs to be replaced by quantum theory of gravity for which GTR is the classical limit. There appear to be only two places where conditions characterized by the Planck scales are realized: the Big Bang, where it all started, and quantum evaporation of black holes. Yet, quantum gravity lies squarely at two frontiers of contemporary physics. The first, a search for a unified theory of fundamental interactions, including gravity, whose simplicity would emerge at energies comparable to the Planck energy. The second is the search for the quantum initial condition of the universe. While quantum mechanics developed between 1900s to 1920s as a fundamental theory of nature, during the 1970s and 80s, a quiet revolution was launched by the design of a quantum world. Researchers searched for ways and means to design quantum systems instead of just accepting quantum theory as an explanation for natural phenomena. Historically, quantum mechanics has been an indispensable part of science since the early 1920s and has been applied with immense success to structure of the atom, nuclear fusion in stars, superconductors, structure of DNA, and elementary particles of nature. Two significant and separate developments guided the development of modern-day computers: the von Neumann architecture of computers and the transistor. Gordon Moore in 1965 stated that the computer hardware would double at the same cost every 2 years. This was possible due to the rapid technological advancements made in the area of computer hardware. But excessive miniaturization threw up a conundrum. We cannot go beyond the atomic scale because classical physics breaks down and quantum mechanics takes over. Laws of physics are ultimately quantum mechanical. It took Feynman's genius to turn a lose-lose situation into a win-win one. He suggested that computers built on principles of quantum mechanics would offset the difficulties encountered by trying to simulate quantum computers on classical systems. The actual start of quantum computing was just an idea. In 1985, David Deutsch attempted to define and subsequently consider computing devices based on quantum mechanics because laws of physics are ultimately quantum mechanics. In 1982, Feynman's seminal paper on quantum computation observed that often it's quite hard to simulate quantum systems on conventional classical computers. Quantum computation and quantum information is the study of information processing tasks that can be accomplished using quantum mechanical systems. The four basic sciences that compose quantum computation are quantum mechanics, computer science, information theory, and cryptography. The bit is the fundamental concept of classical computation and classical information. Qi and Qc are built on something similar, namely qubits. Qubit is short for quantum bit. Just as a classical bit has a state 0 or 1, a qubit also has two states, a ket 0 or a ket 1. But the difference between bits and qubits is that a qubit can also exist in a state other than ket 0 or ket 1. Quantum bits or qubits are used in performing dozens of operations on small computers. Independent of quantum mechanics, a quite new revolution was taking place in the form of Turing machines, an idea put forth by Alan Turing in 1936. So, was he fated for it? The short answer is no. Alan Turing was fully never recognized in his home country during his lifetime because much of his work was covered by the Official Secrets Act. Also, Turing was prosecuted in 1952 for being gay. He accepted chemical castration treatment with DES as an alternative to prison. Turing died in 1954, 16 days before his 42nd birthday from cyanide poisoning. An inquest determined his death as suicide, but it has been noted that known evidence is also consistent with accidental poisoning. In 2009, following an internet campaign, British Prime Minister Gordon Brown made an official public apology on behalf of the British government for the appalling way in which Alan Turing was treated. Queen Elizabeth II granted Turing a posthumous pardon in 2013. The Alan Turing Law is now an informal term for a 2017 law in the United Kingdom that retroactively pardoned men cautioned or convicted under historical legislation that outlawed homosexual acts. The origins of computer science date back to nearly 1750 BC with the discovery of cuneiform tablets indicating that Babylonians had developed fairly sophisticated algorithm ideas. In 1936, Alan Turing developed in detail an abstract notion of a modern-day programmable computer. Turing showed that there is a universal Turing machine that can be used to simulate any other Turing machine. The UTM completely captures the notion of what it means to perform a task by algorithmic means. This assertion is known as the Turing Church hypothesis in honor of Alan Turing and another pioneer of computer science, Alonzo Church. Classical computer consists of wires and logic gates. Wires are used to carry information around the circuit, and logic gates are used to perform manipulations of the information and are also used to convert one form of information into another. This slide shows the classical single bit NOT gate. If the input A is 0, the output Y given by A bar is 1. If the input A is 1, the output is 0. It is very difficult to define an analogous quantum gate or even an analogous quantum NOT gate, but we will attempt to do so. Let us imagine a process which takes a state ket 0 to the state ket 1 and vice versa. What about the superposition state? The quantum gate or the quantum NOT gate acts linearly. It will take the state alpha ket 0 plus beta ket 1 to the state alpha ket 1 plus beta ket 0. You can see that the roles of ket alpha and the roles of ket 0 and ket 1 have been interchanged. The quantum NOT gate cannot act non-linearly. Let us try and understand why. If the quantum NOT gate tries to act non-linearly, it can lead to paradoxes like time travel, faster than light communication, and violation of the second law of thermodynamics. Though we are still quite far away from actually building superquantum computers, we have been successful in implementing some ideas of quantum computing physically. For example, superconducting circuits have been used to implement 2-bit or rather 2-qubit quantum algorithms. Qubits based on nuclear spins have also been used for building quantum error correction devices. Single photons have been used for quantum simulation. The fields of quantum computing, quantum information and quantum error correction are still in their infancy. Technological advancements in nanotechnology have helped realize the dream of Feynman, Turing, Shannon and Deutsch. As and when we can build a quantum supercomputer, what we can do can only be summed up as the sky's the limit. This was a support presentation for quantum computation and design of quantum computers. I hope you've enjoyed listening to me as much as I've enjoyed making it. Thank you so much for listening in. See you the next time.